and went to Turkey and went to ask him, but he was so busy. And he was Western. He would just fly in and fly out the next day and so on. So
one of these guys.
If you're around this week and sit and have a chat about the current state of things.
yeah, it will be great if you have a time. I know that you're probably very busy, but
I have the lecture side after we get to so we can sit down at 4 when we finish. Wanna talk about?
oh, great. That would be great. I mean, so that this you can actually tell me what aesthetics is, what the story is, what the idea is, and so on. So you can guide me through sort of kind of the right direction. I mean, ever since that, in Ralph's papers on CPC with their claim of simulating them with the laser, I was totally confused at how this is possible if you use the total QED, right? I mean, ultimately, that's what the laser is.
It's a bit, those claims are always a bit sketchy because they say, well, I can write down the models and these guys are perfectly well defined time.
Right. So what's going on here? What I was totally confused, and I thought that it's going to be interesting to see where is the issue here, and
it's always we have to calculate for most of these experiments, you can probably see such a change. So you're doing take a system and you take a slice of the space plane, right? And it's the line across the constraint on the set with an overall you get the first stage, right? Right. So there's a lot of time. It's still very interesting, right? So there's this stream of work now that
okay, so all this
causality because for sectors, so they observe that this is experimentally that when you go the sector and a single particle sector and more the polarization, and they say that the way to explain how these experiments look like they interact actually for and the central actually they work out because it looks like they are but really only some sectors something other sectors. So once you look at the sector side, actually on a perfect basis, everything is perfectly.
they've got to do something like that, right?
But you're steering yourself through a slice which has certain properties and it looks like.
Right.
It looks like, but it's because you're putting your interpretation.
But it seems to be that your work we are seeing that is more ambitious in the sense that you're trying to show I mean, it's right. It's like the tracking. So each papers are 70 pages long. Read this in 2 hours.
I can give you this.
Yeah, great. See, that would be great. I mean, it's a lot of coincidence. I feel like I got lucky. It just happened to be
here. Is not a biscuit there.
perfect comment.
It's a new what I do. These days that I made.
You're also associated with pages. That's what a lot of people are into.
There is nothing
with Bob.
That's really that's what
So yeah, but it's
new way.
The categorical okay.
Very smart. I don't want to do this.
That's great. So I will talk to you after
there are things that you have done that
I'm a visitor to Damien Joe. I'm visiting Colorado.
Oh, I see.
Yeah.
These will be where? There is no difference. Although they will use 1%, they don't say.
Just the linguist.
Maybe I'm not know how people think. So no, there's some computers. Hey, how are you doing?
To the transbacks, so
I can see it. So you're already settled here or?
I just moved in under the weekend.
Oh, okay. Well, sir. Okay. That's nice. That's nice. Here's my student. Sorry, my hand is dirty. I'm sorry. So you are in this building, right? You have an office, everything is set. Are you going to do this?
Well, it's just they want to join the meeting.
Okay, good. So, I mean, you should,
Maybe you should also.
Well, the thing is that I'm going for sabbatical.
About
almost
quantum computing.
And so,
But
I would like
to know the human language.
to at least go to the physics department.
So there's a he
So
can
use yourself. And
I don't actually understand.
so that you start studying that is 13 away. Okay.
Oh, you want to? Yeah, I want to.
So what I'm saying is, because I will be 1 year out.
Oh, okay.
Right, okay, but I could be, just connecting and things like that, but physically here.
Well, no, I don't have a camera on me, but yours can be.
Yeah, but if you share the screen there, Mike.
I will share my screen. I'll share my screen. Yeah, it's good. It's good.
Excellent. Yeah, exactly.
So this is a lot of why Cambridge quantum.
So I'll say the same thing. I want you to go there.
They were originally in Cambridge,
Right.
and they moved to. Huh?
You know, there are some people.
That's because they merged with Honeywell.
maybe-
Big, deep Honeywell, big, deep pockets.
You know, this is the kind of.
A lot of money.
He was interested in the gravity.
Okay, shall we? Oh, it's.
Sandro over there. Say hello to us.
Yeah. Oh, yeah, you can. Hang on.
He can hear you.
You can't see me, so I'll just.
By the way. Yeah, you're upside down.
I'm upside down, but I can. Hi, can you hear well?
Yeah, good.
Excellent. Then we'll get started.
The speaker. Yeah, there's one from Italian group. Another from Chinese.
Oh, good. And why? When you want time? It's too. Yeah. Sure.
I don't know.
Oh,
But yeah, so, but there are many other things. But yeah, so I will try before I leave. I will tell the people organizing our seminar, we invite you. Go there, will give you some sort of introduction, who you are, where you're going to be, what kind of thing you're interested in, that you're willing to discuss with people.
Yeah, let's start.
Yeah, that'd be great.
So I
So because it's 2 o'clock.
No, everybody.
We thought we would get started.
If you agree, I'm going to talk to the people and they will come.
Yeah.
Let's see if anybody, yeah.
All right.
Should we start?
Yeah,
I think so.
Okay.
Do we have other people?
check that. So the recordings for this morning.
Recordings are gonna be placed, all of them on this page. If you click on morning for a little bit. This is the video from this morning. And just go in the middle and play some. Yeah.
Yes.
So all the videos
Yeah.
are gonna be on that page. We have 1, there's 9 more to go. This is number 2. So we're not gonna go over the introduction again in the morning. I don't know who else is gonna come. There's pizza and coffee in the back. This is the first lecture on the details, as much of the detail that you would like to.
Yeah.
Very good.
So the very broad plan is for me to give you some examples of how these structures arise. So models, if you will. I'm going to start with simple ones, but you want me to go into the more complicated ones, you want specific examples, you just ask and I'll make it up. Otherwise, I'll sort of start slowly and we'll build up. So this morning I talked about this diagrammatic calculi and secretly what these, I think I can't hear the question, so hang on.
Are you gonna,
Yeah, I can hear you.
are you gonna share your screen? I can't see your screen from here.
Thank you. I think I clicked and I forgot to re-click after. Thank you. Thank you for pointing that out. This is
Don't you get
Then.
this on? Yes, you should.
That's okay.
Set the video so that the ACU.
From the desktop, yes.
Switch to the structure view of the scene.
Yeah.
Doesn't look like anybody can see.
Can see me
Can you do that? You know how to do it here?
With the desktop.
with the desktop. You could, but I don't know if you can with my laptop
Sorry.
He wants to do the slides.
because it's. I think it's a bit harder to write on the.
We tried last night, and if he writes on this, that camera can see him.
But it's a bit blurry
Blurry.
if I write on that. So I don't think that there is a.
Yeah, you're right. I can't, there's nothing.
On
I
the
mean, maybe I
desktop, it's
can-
possible.
Yeah.
It's possible that
Okay,
this.
sorry.
Oh, that's
Sorry.
good. On the desktop, camera works on it.
Yeah, on the desktop, but not on my laptop. Okay, anyway. So let me start with some examples of how you get these diagrams in practice. So if you will, the diagrams are the syntax that you use to write processes or circuits or functions, programs, whatever your specific application dictates. And then in order to get meaning for the diagrams, you have to interpret them somewhere. And you freely mix the two. Most of us do in practice, just not confuse the diagrams with their interpretation, but there is a bit of a separation between them and it's worth keeping it in mind. Still, I'm going to start by saying that the simplest thing that you can represent is a situation where you have boxes and you have a single kind of wire. You have only one type. And the only operation that you can do on this type is to compose things sequentially. So there's no spatial component to it. And because you only have one type, you can always compose things. There's only one wire. Each thing that you have has one input, one output. They always match. So you can only go in a line. And the most basic algebraic structure that supports this kind of diagrams is a monoid. Because if you have a monoid with, what is a monoid? The monoid is some set with an associative composition operation, and associativity is important. And the unit, which is, you can skip it, but you can also freely add it. So who cares? Let's put it there. And then really the sequential composition is defined to be, so the type of the wire is just the monoid itself. And each element, each box is just an element of the monoid. And composition is just a product in the monoid. And if you have a single wire that has nothing, that is defined to be the identity of the monoid. So this is the most basic structure you have. Why is associativity important? Because when you write a diagram, you want to know that you can write F followed by G followed by H without having to remember whether you compose the first two and then the third, or so this has to be the same whether you first apply G to F and then compose with H, or whether you first have F and then apply H dot G to it. So you want these to coincide because you want the semantics of your diagrams. The semantics only have connectivity. They don't remember any bracketing. So in order for it to be well defined, you need to have associativity. So this is associativity of one operation. Single operation, sequential composition is the minimum structure you can use as a monoid. Nothing more, nothing less. Luckily, there are lots of monoids. Actually, you can weaken it in a second. But let's start with monoids have the advantage that you can compose everything. But sometimes you can't. Sometimes you have, for example, functions between sets. So if you take as a model sets with function composition and the identity functions, it will turn out, then you start having a bit more structure because each box is going to be a function, but it's going to have an input of some type X and an output of some type Y, where X and Y are going to be sets, and F is a function from X to Y. And now your composition is restricted. So the type that you use to label your wires becomes useful bookkeeping information. you cannot compose functions unless the middle wire is the same. So you can only compose them when the domain and the codomain match. And so you get that just a wire, if you have a single wire, then the input and the output must be the same. So that's from X to X. A single wire is going to be just the identity function on that set. So it's the function that maps, maybe X was not a very good choice of letter, but okay, little x to little x, that's the identity. And if you have two boxes composed in sequence, then that from X, Y, Z, then that is defined to be the composition of the two functions. So it's the, if you will, it's the function that sends X to G of F of X. That. And now, this is one of the most general settings you can have. In fact, this is probably the most general setting you can have, because every category, as they are called, the structure that allows just boxes and wires and sequential composition, typically you can just embed it in sets. So you can say, you can always interpret the boxes as functions and the wires as sets. That's sometimes useful, sometimes not useful, sometimes it's just a headache, but in principle you can do it. So if you want to be very concrete, you can always just think, okay, there's some kinds of functions and some kinds of sets, provided that your sets are big enough. So given a sufficiently large axiom of choice and a sufficiently large whatever, set theory stuff that we don't have to concern ourselves with. Now, that's kind of boring because there is no parallel composition here. Sets, you have functions, and functions are, I mean, just function apply. But there are some more things you can do with functions of sets. For example, you can say, I look at the Cartesian product of two sets. So I take X times Y. And I look at the functions that go from X times Y to Z times W. And now some of these functions are weird and they mix the two components. So for example, you can look at the swap. The swap is the function that sends X comma Y to, actually, let me write it properly. So you can have swap is from X times Y to Y times X, and sends little x comma little y to little y comma little x. That mixes the components in a weird way. It's not easy to write as a it's not a parallel thing, right? It is taking both of them and mixing them weirdly. Or I can take the C naught, for example. Actually, maybe the C naught is an even better function. So let's keep the swap, and I'll do the C naught after. But some of these functions are factorized. Some of these functions act on the two components independently, in a sense. And so we can take, if we have f from x to z, and we have g from y to w, then we can define the function f times g that goes from x times y to z times w, and sends little x, little y to f of little x, g of little y. And now this function is interesting. These kind of functions that factorize this way are interesting because the two components are independent of each other. Like one acts on the first component of the product, one acts on the second component of the product, and they have nothing to do with each other. None of them depends on the other input. So it might be interesting to be able to write, to have a diagrammatic language that takes into account this kind of parallel structure, as well as the compositional sequential structure of function composition. So we define, we say if we have two wires, x and y, they are defined to just be the system or the identity, if you want, on x times y. So we can now take Cartesian products of our sets. And if we have two boxes, f and g, and we put them in parallel, f from x to z and g from y to w, then this is defined to be the Cartesian product of the two functions. And now this is known as a monoidal category. So I should have probably said this is known as a category. And I'm going to try to keep this language to a minimum because it's not necessarily useful right now, but I will say the right words so that if you then look more into the technicals of this, you can remember what I said and what was what. So this category is a bit richer. It's still sets and functions, so still set with its sequential composition and the identity. But now we have something more. We have the parallel structure as well. So we have the tensor product, which is the Cartesian product, and we have some unit for the Cartesian product. So you have to say what it means when I don't have a wire. And it has to be something which you can ignore freely. And that is going to be some choice of the singleton set. One of them, they're all isomorphic, but we pick one. And we say that effectively, if you have nothing, so if you have an empty diagram with nothing in it, then that's just the identity for the singleton. And we can exploit the fact that X, for any set, X times the singleton set is isomorphic to X, and we can just set it to be equal to X canonically. We can just say, you don't really have to care about these isomorphisms because everything sort of works well. And now these functions that compose this way satisfy an interesting property. You only need to know one property about them, and which is that they slide. So we can apply first G, then F. We can apply them together, or we can apply first F, then G, and we get the same function out of them. So this on the left is F times the identity composed with identity times G. The one in the middle is just F times G. The one on the right is identity times G composed with F times identity. And it turns out that you don't have to care about the ordering. There's this sliding property, which means you can draw your diagrams in any way you like in the plane. So now with this, Gerardo, I'm going to share the slides if you'd like later on. So I see you're taking notes, but
Oh, it's better for me like this.
Okay.
Your way, I can think.
Then you tell me if you don't want me to move to the next slide, I'm gonna ask you before I move. So if you need to finish. Okay. But let me know if you want me to go back to something. Okay. So you have these sort of this structure here, and the reality is you can now write any kind of diagram that has all sorts of functions in it. So you can write things like this, something like that. What you can't do is cross wires yet. So this is known as a monoidal category. It's a category which has a sequential composition structure, a parallel composition structure, but we are not yet free to just move wires around. And sometimes you can't. Sometimes it's good that you can't move wires around, but sometimes it's bad. So this is the monoidal category. And in practice, it so happens that this is only one of the possible choices for parallel composition in sets. There's another choice. That's a fairly obvious one. So you can take Cartesian products and you get functions which act on individual components of a set, but you can take a different kind of operation, which is the disjoint union, and that is also a parallel composition. It's just an additive one instead of a multiplicative one. So you can say, I take sets again, and sequential composition identities. So same compositional structure in sequence, but in parallel, I now look at something different. And I say I take the disjoint union and the empty set. And what happens is that now having two wires, X and Y, is defined to be the identity on X disjoint union Y. So I just take a set, another set, and I put them together. And the parallel composition of functions in this other category, still a monoidal category, but a different one, is defined to be the disjoint union of the functions, which is the function that sends, so this is going to be from X, Y, Z. And this is, I think, good to write explicitly. So F disjoint union G goes from X disjoint union Y to Z disjoint union W. And it's defined to send X in X to F of X in Z and Y in Y to G of Y in W. So it's instead of being a function defined on pairs, it's a function defined by cases. So parallel composition is composition by cases. It's a case-by-case composition instead of being a composition in parallel. And this is also monodal category. It has the same interchange law, but it's a different structure. And the reason I am mentioning this is because when we get to quantum shortly, hopefully, I'm going to say that this is the difference between quantum fields and wave functions. And I'm going to mean it. It's the reason why wave functions don't have entanglement and quantum fields do. It's because one of the structures is additive, one of the structures is multiplicative. And they are they're compositional structures, both of them, but they mean different things. So I'll get there later on. But first, sets and functions, two monoidal structures. I'm going to stick with, I mean, either of them is good. But in the monoidal category, the point is you cannot do this. You would like to say, actually, let me try to, yeah, you would like to say that this diagram is equal to, because it sounds sensible, is equal to this diagram. So F goes into G, K goes down here. They look the same, as in the wires connect to the same things, and in terms of functions, they would be the same. But in a monoidal category, you don't know that this is true, because you don't have any meaning for the idea of what it means for wires to cross. Our diagrams are defined on the plane, and so you can't cross wires. If you want to define diagrams with whatever this just was, what did I do? Huh? If you want to define diagrams where you cross wires, then you have to define what it means semantically, or actually syntactically, to have a wire crossing. And there are two different ways to do this. There's a weaker way and a stronger way, and it depends on how many dimensions you're willing to add. So if you start with diagrams in 2 dimensions, then 3 dimensions, and then 4 dimensions. 3 plus a little bit of 4. You don't need all of it, but it helps. So in 2 dimensions, you can have a wire, and if you try to have a different wire that sort of crosses it, actually, let me just draw. You have one wire, and then you have a wire, it gets to the other one, and it can't cross. There is no space for it to cross. In 3 dimensions, there are 2 things that can happen. It can be that one wire crosses above the other, or it can be that, I guess I could make it slightly more explicit, that, or one wire crosses below the other. So left above right, or left below right. And in 3D, for wires, this is a big difference. I'm looking for 2 wires that I can cross. So if you do this or you do this, it's not the same. Because you can braid things in 3 dimensions. You can take 2 wires and braid them around, and they don't straighten up. They get entangled. They get tangled. Not entangled, but tangled. In 4 dimensions, it turns out you can't tangle wires, because you can always use a bit of the 4th dimension to pass the segment below. You sort of rotate it around the segment above by going in the 4th dimension, if you will. That helps. It's something that there's a history of mathematics lecture series that I did when I was a student in mathematics, first year in Cambridge, and one of the it went from the Greeks, in fact, from a bit earlier than the Greeks, all the way to modern mathematics. And one of the first examples that was given to us was this piece of work by some Greek geometer who said, think about what it means to rotate, to flip. Look at symmetries, okay? So if you look at 2 dimensions, you can do a symmetry. So you can do a mirror symmetry about the y-axis, let's say. That is the same as rotating the sheet in 3 dimensions and then staring at the sheet again, just from the other side. So as in 1 dimension, that's the same as rotating it in 2 dimensions. In 2 dimensions, it's the same as rotating it in 3 dimensions, and then goes on and say, in 3 dimensions, the symmetry is the same as, and doesn't say 4 dimensions, but describes in words what the intuition that would make a 3D symmetry into a kind of rotation in a higher dimension. And this is sort of the same. You're trying to do something which looks like a mirror symmetry on the 3rd axis because you are swapping up with down, but you do this by doing a rotation in 1 dimension higher. So in 4D, there's only one kind of crossing. And you don't have to say which one is up, which one is down, because they are the same, they are equal, or they're isotopic, as people would say. So the difference between axiomatically is that these kind of braidings have to satisfy some property. One of them is, they have to satisfy 3 properties, technically. They're known as the Radmaster moves. One of them is that if you do the crossing and then you undo the crossing, that's just straight wires, so that these 2 maps are effectively inverse of each other. And then the other relevant one is that if you cross 2 wires together with a single wire, that's the same as first crossing 1 and then crossing the second. So these are, they look like they are the same, and it's good that they look like they're the same because graphically they are the same, but algebraically they're not, because this one is decomposed into 4 blocks and this one is just one big chunk. So they are not the same in terms of composing the maps. And this is just these 2. And now it so happens that in the case of 3D, so let me make some space. In the case of 3-dimensional diagrams, it's not true that if you braid things, so if you do the same swap twice, in 3D, that is not the identity in general. Right? Because you have created a braid. But in 4D, the 2 are the same and you don't really have to care. So that's just the identity in 4D. So in 4D, these swaps are self-inverse. And we will not really care about 3-dimensional diagrams because they're a bit advanced and they are useful for things like onions. So if you work with onions in 2+1 dimensions, you expect this kind of braiding relations to happen. If you do topological quantum computing, you expect this kind of braiding relations to happen. And it's very useful to have calculi that keep track of what happens when you braid twice. And that's not the identity. But for the simplest cases, for most of quantum information, you don't need that. So I'm going to go straight to introducing swaps. What does the swap look like in the case of sets? So I said there are two possible structures that we can consider. So I'm going to stick with both examples. One is the multiplicative structure, and one is the additive structure. Any? 1, 2, 3.
There.
Yeah.
Or yeah, I mean, or even the previous one.
Yeah.
So there. So, of course, I understand what they're saying, very clearly explained. But when you go to 4D, 3+1, it turns out that again, we go back to the issue about structure. Okay, what is a structure?
Yes.
If you have fermions or bosons, there will be a difference.
Yes.
So there will be some difference that is related to the structure that is behind.
Yes.
That you are considering as a fundamental whatever. Okay, physical description of your state of your degrees of freedom. So in the question that is natural, I understand because this is what we always learn, that in 3 dimensions, you have the braid group and we can have aliens, whatever. But in principle, I mean, there is absolutely nothing that forbids you to have a similar kind of structure in 4D, 3+1.
It doesn't. You are correct.
We don't know if it exists. That's a separate question. Okay, physically if it exists. But in principle, there is no, it's not forbidden.
No, it isn't. And here I will have to caveat this by saying that taking these pictures physically too seriously and thinking that a wire crossing is truly two particles crossing may not be always the right way to think of it. So it's common in my community to just sell this story as saying it's the tree, the braid is the fact that you can have a face, but the reality is these theorems talk about the diagram, where the diagrams live. The fact that the interpretation preserves the amount of space that the diagrams live in into the space that the physics lives in, that's extra. It might not be the case. For example, in quantum information, you take 4D because you want to have these swaps, but the qubits don't live in any space. You don't care how you do the swap. Maybe you do 3 alternating CNOTs. That's legitimate. So that additional structure preservation becomes interesting when you want to do topological quantum field theory with these diagrams. And then things get, of course, more complicated in 4 dimensions. And the thing that, I guess here I can make that comment, here, we don't have all the information we want, because these pictures, even just in 2 dimensions, I'm going to make a small detour, if you'll allow me, and then we'll go back to the main story. Even in 2 dimensions, even for a monoidal category, you don't have everything you need, because you've left a lot of blank space. But actually, you don't have to. It could be that there are different colors, if you will, in between these wires. And that color is the type, I picked a bad color, sorry. That color is the type of the particles, is the type of the line. So you can imagine, if you imagine anions on a line, imagine 1 + 1 dimensions, then it looks something like this, because you have the charge is associated to some color of the regions. Again, not as visible as I would like. Take green. And here I'm going to take some orangish thing. So imagine that the color is some kind of charge that's preserved for your anions. And then each vertical wire tells you that there's a defect that is traveling in time on a line. So you can really think that this is a situation where, let me do it for 2 + 1, sorry, 2 in 1. So let's say that you have a situation in which you start with a line that has 2 defects or 2 anions on it. I'm taking a super simple model, 1 + 1. And you go up in time. And at the end, you have only 1 anion on it. And the charge on the left of this anion is preserved, and the charge on the right is preserved. But something happens to the 2 anions in the middle. They live their lives, and then they interact in such a way that only 1 anion is left. They fuse, for example, in some way. And this kind of operation has to be consistent with the charge in between them. And there's a bunch of conditions that you might want to put. And those conditions are captured by this structure, which is a 2 category. So it's like a monoidal category, but where you add information on the space. And knowing that you have to add information on the space tells you that you're missing something when you go 1 dimension up. Because now it's no longer about having wires in 3 dimensions, but it's about having wires in 3 dimensions plus color on the surfaces plus color in the volume. And now you want to do it in 4 dimensions. It's wires in 4 dimensions, colors on the surfaces, colors in the volumes, colors in the 4 volumes. That would be the equivalent of a 3 + 1 topological quantum field theory. And the structure that comes with that is much more complicated. So you have all of these additional considerations, such as you could in principle have swaps that don't work, as they don't self-invert in 4 dimensions, is true. And it's because the categories you're considering are no longer monoidal, but they are 3 categories or 4 categories. So these sort of operations carry a lot more structure with them. And you can see it in the simple case of monoidal categories, because you already have this idea that if you add color to the space, to the sheet around the wires, that gives you a different structure. So these are 2 categories that they're a richer setting. But in quantum information, you typically don't want to care about where the qubits are. You just want to care about the qubits. In set theory, you don't care about where the sets are. You don't even care about the order of the sets typically. So that's just additional information you don't want to keep. And you just care about the operation applied to them. But yes, in topological theories or condensed matter theories, you have this additional bookkeeping that you have to do, and the structure is more complicated. I can go in more detail later on if you like.
No, that's fine. That's fine. So the question is, in many of these structures, okay, what you call three-dimensional,
Sure.
In many of these structures, you can map algebraically to a Fox space type of structure.
Mhm.
I want to think in terms of quantity.
Mhm.
So when you start thinking about, TQFTs, with additional structures and more complicated structures, is there any simple way of constructing a Fox space for this part?
For some of these, well, TQFTs are particular.
Because I know how to do it,
Yeah,
but in general.
there are some constructions of abstract Fock spaces. There is none that would give you answers that sort of the quantum field theorist wouldn't already kind of know yet.
You'd be surprised. You'd be surprised, for example, if you take parafermion, okay, and now you construct Fock parafermions in a Fock space. So why you want Fock space? Because in physics we use detectors.
Yes.
So you want to count the particles with
Of
a
course.
detector. Okay, so that's the reason why you want Fock space, because there is a number operator that you can define, and then the detector is counting.
Yeah.
Okay, like one part, two part, three part. And it's not innocent that if you want to use a detector to detect those particles and figure out that those particles exist in nature, you will need the sort of, or the equivalent of a Fock space, because it's not obvious, how to count.
Yes.
Okay, so and those constructions are not obvious in any possible way.
No.
I mean, that's the reason why I'm asking if people thought about those things, because I gave it some thought about that, and I can parse a solution, but a general solution.
I don't think
it's hard. To me, it's
I don't think there is a general construction. There is a stream of research that characterizes Fock spaces as exponential modalities on some of these categories. As in, you say it's the same as saying that you have a type and you generate the Fock space type by saying I can have 0 or 1 or as many as I want. I can just repeat the number of particles of the type, and that gives you an exponential modality or a bang. But that's very specific to some of these settings. It's not general. I also know that there is research on constructing categorical Fock spaces for some of these higher categories, but I'm not entirely familiar with it. However, I can go and dig it up, and tomorrow I can maybe send you a couple links. Of course. Okay, so back to my original two categories, two structures, two parallel structures here that we can consider. One of them is additive, one of them is multiplicative. They give you, I can give you two swaps. So the swaps are typed x, y, y, x. They just have to swap the two. One of them has to send x plus y to x times y, sorry, to y times x, and it sends little x comma little y to little y comma little x. And the other one has to be a function defined on a case-by-case basis that goes from x disjoint union y to y disjoint union x, which is the same as x disjoint union y. So in this case, it's actually really trivial. And it's just the identity. So it's kind of funny. And it sends x in x to x and y in y to y. So what is this? This is just the identity function. There's no swap in here. This is a commutative category. It's one where the monoidal product gives you the same object both ways. So the swap is the identity, which is kind of, it's a very strong statement. But this is just the identity. Now, more structure. And now we get out of sets because we have to at some point leave the comfort of this category. We've been using it for too long. I want my category to be able to have bends in my wires. I want to be able to say that it makes sense to take a box and bend the wire around. And I want to be able to write something like this. Or I want to be able to write and prove obviously this is identity. I want to be able to write a function and trace, as one says, an input and an output. I want to be able to do all of these things or some of these things. And I wonder what the additional structure necessary is for this to happen. So I want to, let's say F, I want to be able to do this and so on. So state effect duality, I want to have traces, I want to have the snake equations, I want them to behave well. No, that's the same. Sorry. Outer snake equation, thank you. So how do I do it? Well, in sets, there is no way to do this. There's just not enough structure in sets. Why? Because we can ask a simpler question. So say that we want to be able to write this question mark. Can we do it in set? Can we find two boxes in set? Let's say a set with the tensor product. So from now on, I will work in set with the parallel composition taken to be the Cartesian product. So it's kind of like quantum. And I want to ask, can I find boxes that do this? Is this something which happens? And the answer is surprisingly no. And the reason why it isn't is that there is only one kind of box that goes from any set X into the tensor unit. So this box is always the function that sends all X to the singleton element. This is the terminal box, and we denote it by this ground symbol. It's the discarding map. And it turns out that in set, the only way to get these effects is the discarding map. Set just doesn't have effect. There are no questions you can ask in set. There are no scalars in set, in fact. The only scalar that you get is the scalar 1 or star, if you want. So I'm going to change this into 1 because it will make sense soon. Actually, no, let's give it star. Why not? There's only one question you can ask. The trivial question. There's only one answer you can get. The trivial answer. There's nothing interesting in it. There's not even Booleans. Okay, so that's kind of boring. And indeed, if we look at this particular map, presuming that we even have a cup, which we don't, but even if we could find one, this would completely disconnect. And so it can't be the identity because you forget what the input was, so it can never be the identity. So this is certainly not the identity. Okay, so set is not, as we say, compact close. In fact, but there is a simple extension that I can take, which is compact close. And this is, instead of having functions, I take sets and relations between sets. Instead of saying that F, a box from X to Y, is a function from X to Y, I say that F is a subset of X times Y. It's a relation. Or if you really want to make it interesting, it is a Boolean matrix. Because relations are Boolean matrices, right? It's just you're composing Booleans with or and and instead of composing complex numbers with plus and times. It's the same thing. So this is the same as F is in 0, 1 to the X times Y. So it's a matrix or Y times X, I guess. If you want, it's a matrix, but you can think of it as a relation. And okay, this is good because relations have a lot more things in them. First of all, the tensor unit for this category, which is called rel, composition of relations, the identity function, Cartesian product, and the tensor unit, which is still this singleton. But there are two scalars now, 0 and 1. So you can ask questions and get answers. The answer can be yes or no. So if you look at the relations on the tensor unit, they are the tensor unit and the empty set. So the tensor unit is going to be called 1 and the empty set in it is going to be called 0. So we now have two things. We now have two answers, much like this is the same as having complex numbers, but we have a simpler setting in which there's no complex numbers. So now composition of relations is just the usual composition of relations, but we get cups and caps. So what is the cup? The cup is something from the tensor unit to X times X. So it's a relation. It's the relation that puts in relation the element of the singleton with the cup with the pair XX for all X's. So it's the relation, is the subset of the relations into something are the subsets, exactly the subsets of the set. So it's a subset that consists of all pairs of identical items. And the cap has to be the other way. In fact, it's adjoint in a very, or a transpose in a very sense. And it's the function that sends, it's the partial function that sends x into star for all x in x. This is a subset of x times x, and this one is a partial function from x times x into the singleton. And now this category is compactless, and I can prove it fairly straightforwardly, because like all I have to do is prove the snake equations. How do the snake equations work? Well, again, we draw the snaky thingy, we decompose it as parallel and sequential composition of things, like this. And so we ask, what are the relations that are involved? Well, the one at the bottom is going to be the, again, x and x. So this sends little x to little x, little y for all little y in x. The one at the top is the one that sends little x, y onto y for all x. Actually, x and y in x. So those are the two relations. I just took the Cartesian product. And now if I compose them together, I get that little x, this one, I'm going to use a color to do it. So you enter here, you go here, it's equal to this one. You go down here, it's equal to this one. You go up here and you get out. So the result is of this composition is just x into x for all x in x in big X, which is the identity. So indeed, it's true that snake equations hold. This category is compactless. So now we can talk about relations as a way of saying functions plus traces, function plus time travel, functions plus fixed points, whatever, however you want to, whatever semantics you want to give to this, it's something that you will be able to interpret. So you can really think, what is this function? I take a function f and I trace part of it. What does that mean? Well, that means that I have taken, this is now a relation. In fact, it's going to be a partial function. It is going to go from x to y, and let's say that this is z. What is it? It's the, it maps x into f. Okay, I guess it maps x into the first component, or the component of y of f of x z, component on y, for some z such that f of x z is. So it's the, you take a fixed point and you apply the function to some fixed point of itself on one side only. So it's a partial trace or a partial fixed point. And this is now, it's a partial function. This is going to be a partial function, because for some x's there might not be a suitable z. So it finds a fixed point of this operation. Now, great. So this is sets and relations. That's an introductory version. Let's move on to the, yeah, sets and relations.
What does it mean? Because the cap and cap in the usual category that we use for quantum computation has a meaning of it's either in Cantor state or it's either a projection. It's a Bell measure. So what is the physical interpretation of this cap and cap in this red thing? What does it mean? Because it looks like more is like some sort of classical probabilistic. What it is exactly, what it means physically?
It's not probabilistic. It's possibilistic. It's that, yeah, that it is, instead of asking the question, how likely is it? Think of classical systems, and now look at the classical system and say, instead of asking the question, what is the likelihood that this happens? Ask the question, can this happen or not? So you take a stochastic matrix, okay? So give me your favorite stochastic matrix, 2x2 stochastic matrix. I don't know, it sends 0 to 50%, 25%, and it sends 1 to 50%, 50%, something like that. So this is definitely a stochastic matrix. And now I say, okay, I really don't care about what. In fact, let me give you a one which has a 0 in it. So otherwise, it's boring. Stochastic matrix. It sends 0 to a mixture of 0 and 1, 75, 25, and it sends 1 to 0. It's just a map. And now you forget about the probabilities, and you map all the x's. You map 0 to 0. And you map x greater than 0 to 1. And what you get is this matrix. But where here the operations were plus, this was in the positive reals with plus 0 times and 1. That was the semi-ring that supported this matrix, because the matrix, in order to do matrices and compose them, you have to have at the very least a commutative semi-ring. That's the minimum amount of structure that you can use to write a matrix, because you need to be able to do sums and products of the elements, and the order in which the sums and products are taken cannot matter. In fact, you can do it with the non-commutative multiplication, but it's a bit more complicated. You can, but you have to do a bit of bookkeeping. But let's say commutative semi-ring. What is the commutative semi-ring on the other case? It's the semi-ring with just the booleans. Instead of plus, you have or. You have 0 and 1. And now this mapping is a homomorphism of semi-rings. So it preserves matrices, it preserves matrix products, it preserves sums. It's just you replace the question how likely this is with the question can this be? So it becomes a possibilistic setting. And it is sometimes interesting to restrict to possibilistic settings because you can prove some stronger results in that. You can use this morphism to say, if I had, let's take the non-locality in quantum theory. There are some non-locality scenarios that depend on the exact probabilities. And then there's not much. Bell scenario. Bell scenario has specific probabilities and the correlations work out. But you can take some scenarios such as the, let's say, Mermin scenario. Mermin is very strong, but let's take Mermin. In Mermin, you don't even care about the probabilities, it turns out. You can say, take the probability for the Mermin scenario, forget about the probabilities, and only remember what can happen and what can't happen. And that is enough to prove non-locality on its own. So it's a stronger form of non-locality. Because if you have a local hidden variable probabilistically, then you can forget the probabilities and you get a possibilistic one. So if you can prove that there is no possibilistic local hidden variable, then there is no probabilistic local hidden variable. So this kind of forgetting and working just with relations helps you simplify some of the arguments and get stronger results because they sort of pull back through this functor technique. So it's a lax functor, but still. So it is a useful toy setting, and it helps you reason about what is necessary and what isn't necessary for some of these quantum arguments. But it's a toy setting nonetheless. So if we go to quantum, let's see, given that we are in the place, the thing is, it doesn't really matter whether you have complex matrices or Boolean matrices or real matrices or really any matrix over any semi-ring. So if you have a semi-ring, S, I'm going to say plus 0 times 1, and you consider the matrices. So you type your wires as Sn, Sm, and you say that F is just a matrix. It's an M by N matrix in this semi-ring. So it could be that S is the real numbers, positive reals, all the reals, complex numbers, the Booleans, whatever. This is nice because it gives you a possibility of working in quantum theory, but also in real quantum theory in probabilistic models, so stochastic matrices, but also pseudo probabilistic models. So the ones with the negative probabilities that are used to define these sort of pseudo hidden variables for quantum systems, and you can prove that they always exist, for example. You can do possibilistic arguments, you can work with tropical semi-rings. Yes, sorry.
Looking at semi-ring, how do you solve it? You don't have some kind of a limit structure.
You do, yeah. Because you don't have the semi-ring, right? You have the matrices over the semi-ring. And these are always finite dimensional. These are finite dimensional modules over the semi-rings. So you can always just do the sums and they're always finite. Yes, the problem becomes the moment that you introduce an infinite dimensional object, which in REL you have. So in REL you can always do it because REL has this quantile structure that handles arbitrary sums, if you will. In general, you can't. And indeed, in infinite dimensional quantum theory, writing what it means to have cups and caps has been a problem for a long time. Now we know how to do it, but we have to use infinities. Like you have to use algebraic infinities to solve it. So it's non-trivial. But these are all finite dimensional. So n and m are just natural numbers. So I'm going to make my life easy. These are proper matrices, not infinite matrices. But yeah, excellent point.
Yeah, the physical way of distinguishing, for example, category REL.
Yeah.
It's consistent with, let's say, do some experiment, you are agnostic about, what is the structure. You see that there is a violation of some, Mermin inequality or whatever. Let's assume that, this type of category, which is not the usual category that we would use for quantum mechanics to explain this outcome. Is there any way of falsifying which of these things, which experiment you have to do to distinguish between these?
Yeah, you can. Mostly so REL doesn't have an interference.
I see.
Because
So
OR is not cancelative, so you cannot see any interference ever. There's no interference effect. You always get the OR doesn't have a cancellation law, so you cannot interfere things away. But there is no way to distinguish the complex version of quantum theory from a local hidden variable that allows negative probabilities. So you might say, I live in a world where negative probabilities exist, I just never see them. That is perfectly consistent. There is no problem there, but the only question is it useful in any way? The answer is no, that's a legitimate. I'm saying there are sometimes you can distinguish, sometimes you can't. But one way to say I don't live in a world which has negative probabilities is to say I never observe negative probabilities. So if I do, I certainly cannot do all experiments in this particular category. But to disprove that you're in REL, all you have to see is some kind of interference between your operations, and then it can be REL. The moment you see that it was possible here, but it becomes impossible when you rotate it, then it can be REL, because REL preserves this. Once you're in one, you're in one. That's it. Once it can be, it can be. So that's a 3/4 of an answer. No.
If there are other possible structures that maybe are more reasonable and can explain the same set of experiments.
Yeah, I mean.
All right, but what I'm saying is that, I mean, we in physics, what we do is we have some structure in our mind. We try to falsify in some experiment, right? But there may be another, but in this particular case, quantum mechanics is weird. So the question is, maybe there are more, other structures, and people have been thinking about it, of course. Other simpler structures that, essentially explain all the same experiments that you can explain with quantum mechanics. But then the question is, what is the experiment you have to do to falsify this structure compared to the structure of quantum mechanics, standard quantum mechanics?
So from the point of view of categories, this is a stream of research that's known as reconstruction theorems, whereby you assume some physical axioms, some principles that you'd like your theory to satisfy, things that you've observed, and you say, can I, from this principle, derive that the only model consistent is quantum mechanics? And there are a few of them, and they take slightly different principles, slightly different like information preservation, parallel processes. So slightly different flavors of what it means to mesh the physical observations. And then they work out that the category of positive matrices over the complex numbers is the only category that actually reproduces those results. And there's quite a few of these results, not lots, but maybe a dozen or so. So there are ways, depends on what you want to assume. And if you don't assume enough, then it turns out that there are models compatible with quantum mechanics that are not quantum mechanics. Like if you are a bit too conservative in your assumptions, you have all of these results about which Born rules work, for example. And it turns out that the usual Born rule is not the only one unless you make some fairly strong assumptions. So there's theorems, and it depends on how much you want to assume, I guess. But there are categorical versions, and they are technically called reconstruction theorems. So once in a while, someone puts out a paper that says a new reconstruction result for quantum theory, and that's what they're doing. They pick some axioms they liked, and they prove that the only compositional structure compatible with those axioms is the category of positive matrices over the complex. But for any semmering you can compose matrices, you can take the Kronecker product of matrices, and those give you one of these monoidal categories. In fact, they all give you a symmetric monoidal category. It's always one. And they always have the same structure, they always have the same swap, they all work the same. So you can pick, in particular, matrices of the complex numbers. You get a trace, matrix of the Booleans, you get a trace, and so on. What I wanted to point out is that for complex vectors, there are two structures that are available. You can take matrices over the complex numbers with matrix composition, matrix identity, which I'm just going to write one. And you can take the Kronecker product and the complex numbers themselves as your, actually I should have said CMAT. And this is the last remark I'll do as part of the main lecture, but we can continue if you would like after. And I can take this other version. So this is going to be called, this is the multiplicative version if you want. And then there's going to be an additive version. And what's interesting is that it doesn't work the same way at all. Where you take the direct sum of Hilbert spaces, or the byproduct, if you want, and you take the C0, so the space with only one element in it, as your unit. What do the states look like in these two products? I think that's the main intuition for me. If I take the Cartesian, the Kronecker product of two states, let's say 1, 0 times 1 over root 2, 1 over root 2. So I take 0 times plus 4 qubits, let's say the simplest example. Then what I get is a state that looks like 1 over root 2, 1 over root 2, 0, 0. If instead I take the additive parallel composition of these two these two states, and I pick 2 because it makes things interesting on its own, but I'll take 3 later. You get 1, 0, 1 over root 2, 1 over root 2. Because what you've done is just stick them one after the other. So it's easy to get a little confused at the start, but one of them is the nested state where I have 1 times 1 over root 2, 1 over root 2, and 0 times 1 over root 2, 1 over root 2. And the other one has the two states one after the other. So it's 1, 0, 1 over root 2. So one is additive. And the way that you see that one is additive and one is multiplicative is if you try to do it in general. If you have Cn tensor Cm, that is Cn times m. And if you have Cn plus Cm, you have Cn plus m. So one is additive, one is truly multiplicative. What do they mean physically? Well, this one means that you have two particles in a tensor product. So let's say psi and phi. And if you take the tensor product, these allow entanglement. So you can, for example, write the cup. You can have the Bell state, which is this one. So this exists in the case where you take the multiplicative structure. So this entanglement exists. This allows. In the other case, when you take the direct sum, what you get is just a vector that has both components. So you're just taking the indices and making wave functions over them. So this is actually the wave function space. So if this is C to the A and this is C to the B, then it's taking A, this region, B, this region. This is the part that's psi. This is the part that's phi, and you're joining them in the middle. You're taking the disjoint union of the two. So this is just the gluing of wave functions. While these are fields. And indeed, you get two different structures, and I'll conclude. In one case, if you take the full tensor product, and you will forgive me, if you take the full tensor product over, let's say, a lot of vectors over all the points in some position space, for example, you get fields over that space, and in the other case, you get wave functions over the space. So that's not the same structure, and you see it both in finite dimensions and in infinite dimensions. And the second one does not support entanglement at all. There's no entanglement. Why? Because it turns out that this structure on the matrices, so if you take CMAT matrices, complex matrices, composition, identity, direct sum, and the space, the trivial vector space, you have some maps which copy things and co-copy things. So it's a Cartesian product in a sense. You have the projectors on the individual components. You have, it's a byproduct, right? So you have from X and Y into X plus Y, and then back into X and Y. You have the two products, and you have the two injections. And this gives it, because it's just saying that you can take any matrix and you can always sort of make the block matrix for it. And which is really the structure here. And here, what you have is an observation that you cannot have entangled states just because all the states necessarily factor. If you have any state that goes into direct sum, what is happening? Then it is always equal to pi 0 and pi 1 injected back into the direct sum. So there's no entanglement ever. Yeah. I can't see the. Yes. If you have any questions, the volume is up, so you can just ask them. I can hear you.
I have questions.
You have questions. Shoot.
So what is the physical realization of this additive category?
It's just it's vector spaces. It's quantum systems with the additive products. So it's quantum systems where you say that you do operations on a sectorial basis. So you imagine that you have a system that's on a space which has two pieces in it. So you have a wave function, let's say on a segment where there is a small segment X and a big segment X and a smaller segment Y, and doing an operation in parallel on these wave functions means that you do something on the X sector and something else on the Y sector. So you transform them independently. So this one, you apply some unitary to it. And here you apply some unitary to it. And again, it goes onto some other sectorized space. So it's doing the block matrix. So a map F, this joint union, I guess plus, let me write plus.
Right, but you're making, if I understand correctly, you are making a map between those sets and space.
those are vector spaces. It's direct sum of vector spaces.
Right, but what I'm saying,
Actually, I guess.
physically, in your viewing those states,
Mhm.
you're doing is you're making a map. You have two, like, you have Cn plus Cn.
Yeah.
We're saying that Cn is associated to a particular region in space.
Yeah.
And the other is associated to a different region in space.
Maybe it's a space, maybe it's a different sector for some
It can
other,
be any color,
anything, any sectorialization of a quantum system that you'd like. So super selection sectors are like that.
Sure, but let me ask you then the question different. What is classical electromagnet in this time?
In what sense? That's a very
What is
broad,
it
that's an
actually?
incredibly broad question.
Yeah, no, it's broad. It's broad. In fact, let me reformulate the question. If I were to look for the category that is associated to classical electromagnet, Maxwell
Mhm.
standard, theory that has been used for centuries.
Yeah.
What centuries now? Centuries.
Yeah, or century plus. Yes, yes, yes.
Century plus.
That's it.
What is the category associated to that?
So it would
So
be,
what I want to have, let me tell you what I want to have. It's electromagnetism. I want to have fields. I cannot have fields. There is interference, but there is no tangent.
so it's going to be the category of L2 spaces over some subsets of some suitably nice subsets of the three-dimensional space, flat three-dimensional space, so R3,
Let's assume.
with the disjoint union of the underlying regions. That would be the fields over that. Actually, L2 only gives you one component, but some direct sum of classical field spaces over that. So you typically do a direct sum of whatever value space you want to have, because electromagnetism is not one component, it's multiple components.
Oh, no, yes.
Just,
absolutely.
yeah, but it doesn't really matter. Here I wrote C, but you can write, here I said C, but actually you can write direct sums of anything you want. It's called a direct integral, right? It's von Neumann's direct integrals. So you can write any kind of spaces you'd like. And you can integrate over any measurable space. So it doesn't have to be finite. These things are very well defined in literature. People know how to write them. And you can say it's the space of fields over a compact region of space-time, for example. And that's well-defined Hilbert space. And the direct sum is just the disjoint union of the underlying regions. So it's the property that says that if you take the direct sum of two of these spaces, so let's say Y in X, H, Y, then you get the direct sum over the disjoint union of the two spaces. And that just says that you've effectively glued together two regions, and now you allow a wave function component on one, a wave function component on the other, and you can act on both. You can act on each one independently. It depends. So if you mix them, then your map is not gonna factor, right? It's not. Your states are always just elements of this vector space because they always decompose as a wave function on a region and a wave function on the other region. Whether that category is nice to work in is a different question.
No, the question is started there. The question continues, but I don't want to capitalize the discussion. The question continues.
All right, so let's start with that.
Actually, I have a question about this. So if I have two particles, let's say 1 and 2, I have two Schrodinger equations with that.
Yeah.
Right. And if I keep the coordinates of these particles like different, let's say R1 and R2.
Okay.
That is essentially what you mean by this.
Just one, so it's point-like particles. It's on one.
Yeah, it's
Okay.
a wave function on R1 and a wave function for R2.
Yeah.
And I just glued them together. So that is an example of your direct product.
No, because two particles, if you glue them together, two particles are in a tensor product space. They're not in the direct sum, right?
Unless they have the same X, the same R, the same coin.
If they have the same coordinate, you have, let's say you have two photons on the same point of space.
Yes.
But then
But I
the,
consider them.
or two electrons, or yeah, two electrons with I don't know, two bosons, but with additional degrees of freedom that allow you to distinguish them.
Right.
Okay, so distinguishable but on the same place.
Right.
Yes, that's a direct sum, because the Fock space is direct sum of the sectors, right? Of the number of the degenerate sectors of the number operator, which in your case would be more than one dimensional, because you have more than one particle can have more degrees of freedom. Let's say you have a qubit degree of freedom per particle, then your Fock space is just the sum of qubit times n. So it's L2n times the qubit. But sectorialized as 1 qubit, 2 qubits, 3 qubits, but they're distinguishable because you made the distinction.
Exactly, yeah.
But then if you want to actually model the subspace that only considers the bosons, then you have to take the symmetrizer of that. So you have to sort of symmetrize, and you have a smaller subspace.
Let's say that every possible linear form, some cases, is an allowed linear form. And now if I try to impose this theory on a composite system, entanglements of everything.
It depends what you mean by composite system, because there is no one choice of what the tensor product structure is, which I think was Gerardo's original point this morning. You have to pick one, and different structures give you different notions of what it means to work in parallel. In the case of sets, you have this idea that you can either define functions in parallel or functions by cases, and those are both kind of parallel but different. In quantum systems, you can either think that parallel means acting on different states simultaneously, as in independent particles, or you can think that it means acting on different sectors of the space simultaneously, so on the same wave function, and that those two things mean different things.
Different sectors of the space,
Hang on, let me give you an actual. So you have two unitaries. You can either take the tensor product, or you can take the direct sum. One of them is U00 times phi, U01 times phi, U10 times phi, U11 times phi. The other one is UV. Like that. So in the first case, you have U acts on one particle, V acts on the other particle. In the second case, there's only one particle, U acts on one sector, V acts on another sector. So say that these two are, for example, the even and odd sectors of some mirror symmetry, for example. So the bosonic and fermionic sectors, something like that. Or they are different energy sectors. You have two energy levels in your system. One of them is the ground energy, one of them is the excited energy sector, let's say. And then in parallel, really just, it's not the notion of parallel that you necessarily think. And there is a way to characterize which one, I mean, why they come about. And that's a bit of a longer story. If you're interested, I can go about it, but maybe after we exhaust all the more standard questions. You said you had further things.
That is big,
Shoot.
because my question is, the next obvious question is, if you can identify a category associated to classical electromagnetism, the next question is there any model of computation that you can develop based on that category? Okay, and I'm not talking about, just using the physical system to operate as a Boolean machine or operate as a quantum computer. No, that's not what I mean. What I mean is to operate as something that is different. Okay, something that is a different, also universal model of computation, but that model of computation is not using entanglement, but is using interference.
Maybe, but
I'm pretty sure you can, but it's not obvious.
It's not obvious to me how, but yeah.
It's not obvious how, but this would lead to an optical computer.
I see.
Which is not the same as what they mean by optical computer, because what they mean by optical computer now is to be the computer that is using optical components, but to realize a Boolean logic. And that is trivial in some way. From a foundational point of view, it's a trivial thing. But to construct an optical computer that is realizing a wave logic is not the same.
So the idea would be that if you, these are always these are both descriptive languages and reasoning languages, but the kind of reasoning you do depends on which axioms you put on the fundamental building blocks you pick.
Exactly.
So if you pick the right building blocks, then you might be able to find that working with them gives you a notion of computation like the one you described, but you might just pick other building blocks in which computation is something simpler or more boring, still universal perhaps, and you can still describe everything, but maybe not with the same complexity, because the complexity depends on what you pick.
Absolutely. So I want something universal, okay? Something universal that let's assume even it could be that, you know, the Boolean logic is embedded. Okay, the Boolean logic is inside that logic I'm talking about, because that's enough. Now then the big question is, how can you realize this experimentally? That's a separate question.
That's
because once you have your, I mean, of course, an important one. Okay, I mean, I'm not saying it's not an important one, I'm saying it's a separate question. Because then if you have that structure, you have the mathematical structure, then you can think, how can you physically realize that particular, there will be some gate that is exploiting interference. Okay, and that is a gate that will have to be thought physically how to be.
Yes.
Okay, so to go to an engineer and say, this is what needs to be done with photonics or whatever.
So there is a presentation, for example, of the, there is a presentation of photonics that uses a finite set of parameterized gates, at least for the Gaussian states, it's well understood. Then you introduce one non-Gaussian resource, and you know that you can in principle get everything. But the axiomatization of what happens when you have a non-Gaussian resource is not, I don't think it exists yet.
No, that's
so nobody has yet figured out a finite universal set of rules that tells you just physically what would happen if you compose these boxes in any way. And of course, at some point, the calculation cannot be that it's easy to do, because otherwise the quantum computers that use it to perform universal computation would be easily simulatable. So that's actually an interesting point about all of these languages. They cannot simplify your calculations too much, because if they did, you could just use the rules of the language to simulate the calculation and you'd be done.
Yeah.
So there are some bounds on the expressive power, of course. They're the same bounds that linear algebra has, except that linear algebra is very uniform in its bounds. Everything is always exponentially sized. You have like your states are fully expanded, your matrices are fully expanded. So you never have a situation where some operations are easier than others. Technically, they're all exactly the same. All matrices have the same, maybe there's lots of zeros, but if you forget that the zeros are easier in some sense, you don't know any block structure, you have to still do all of the products and all of the sums, and it always takes the same amount of time. Instead, with diagrammatic reasoning, which we'll see in the coming days, some operations are easy to write and therefore easy to compute, and other operations are hard to write and so harder to compute, perhaps. And you effectively, by picking some generators and some relations between them, you select a class of processes that you find interesting and you want to be faster at calculating, and other processes maybe are slightly harder to, not necessarily they become harder to work with, but if these processes are the kind of things that you use to write quantum circuits, for example, then that's it. Or if they are, say, if you want to write how quantum systems evolve, then perhaps it's good to have simple building blocks for the kinds of Hamiltonians that you care about. That's something that I've been working on, that people have been working on. There's various choices. Different languages give different results, I think. But the question of the complexity of computation from the languages is open, and people have kind of looked at it, but not really. Certainly not in the case of something infinite dimensional. Nobody touches infinite dimensional stuff if they can avoid it.
My question is a question it's pragmatic, because it's related to the possibility of building a new device that is not functioning in the way that we've been thinking about computation. It could be much more powerful than what we have right now. It's just an issue about advancing technology. a little bit. It's not that, what I'm saying is not that the hurdle is, you know, like defeating the coherence or anything like that, that you have to go to very low. No, it's figuring out how you can generate interference, a device that explodes interference.
So
That's it.
the way that these languages typically help with tasks such as figuring out new protocols or new devices is they give you a faster, simpler way of looking at the structure of your processes. So obviously they cannot give you any answer. The basic building blocks that you put into the theory cannot give you any answer that you didn't already have, because in order to define the language, you have to say, I have these building blocks and they obey these relations that I understand. So that you have to understand. But those building blocks don't necessarily give you anything you want yet. What they do give you is a way of reasoning about the processes that can be composed out of those blocks, like Lego, quickly. As in, the human brain is not huge. I mean, some brains are big, but still very finite, and we are not very good at keeping complex structures in our heads all in one place. We don't really see them very well. So having calculation tools that allow you to see more structure without having to look, like stare at the algebra and go 5 meters away and hope that it coalesces into a picture of what it should do, then that helps. It helps to understand quantum algorithms. It helps to understand quantum protocols and information theory. It probably helps to understand these kind of machines as well. But you have to pick a good set of basic operations. So you have to have someone who has the knowledge about the kind of technology or the kind of behaviors that you can exploit. And then you compose the behaviors and you figure out a way of making what you want, maybe, because maybe you can't.
So what I'm talking about is mostly whether, you know, this kind of math can help you get to that.
That is my experience of learning quantum physics and quantum computing and quantum cryptography has been that it would have been much harder to get the understanding I got in the years just looking at the algebra. As in, I had to, because I had to read papers by other colleagues or authors who are not using these languages. And it was most of the time harder for me to get to the intuition using the explicit linear algebraic methods than it was using the diagrammatic methods. But that's also because I looked at very specific problems for which either the languages existed, or if they didn't exist, then I worked on making the languages. So I first got the language to talk about them, and then I looked at the problems, and they became easier to work with. Not everything is, but I think it's also true that you don't necessarily have to have one language. You can have languages that tackle different aspects of the problem better or worse. So for example, the ZX calculus is fairly famous now. It doesn't work well. It does work for everything because it's universal and complete, but it doesn't work well for, say, your traditional quantum algorithms, Gogioso or factoring, or the one for Simon's problem. Because they rely on the classical structure of these Boolean oracles, you have a lot of these AND gates. And AND gates in the ZX calculus are not particularly easy to work with. You can write them, you have axioms that allow you to do all the reasoning, but they have many pieces that fly around, and you have to be sort of you have to have discipline in the way you manipulate them. And so you can either say, I train myself to be disciplined, or you can say, my discipline is the definition of a new language that sort of encapsulates the complexity into some new boxes. And I forget what they look like until I really have to. And you can, because these languages can be like expanded and mixed in any way. And so people invented the ZH calculus, which has these H boxes, which make it very easy to talk about Boolean stuff. In fact, the entire calculus is based on Boolean axioms, effectively. And then it's easy to talk about these algorithms, but not easy to talk about the other ones necessarily. And you just pick the ones that you want for the application at hand. So electromagnetism, if you have some basic operations in mind that could be building blocks, you can model them as generators. You can write down rules that you know they satisfy, like the ones from photonics, let's say. I'm saying akin to the ones from photonics. And then you start trying to write down processes with these and see what simplifies what is equal to what. And I think that is typically the way in which this kind of techniques help discover new things. They just make it very easy they just make it fast and easy to go from A to B. So you discover more just because you have more time, in a sense. It takes less to do the calculation. So they do tell you, for a mathematician like myself, an abstract mathematician, they can't tell you anything that you don't know already, in the sense that the moment you put the rules in, the rules already imply everything. But the process of discovering what they imply, that's the road. You don't know that they imply everything.
This, this theorem that takes any unitary matrix, as in terms of one qubit and two qubit gates, all these detailed results are fundamental.
Yeah.
Because you need in order to build the whole thing. So I think what is equivalent of that thing in the case of an optical wave logic is not obvious.
No, but that would be the starting point. Yeah.
Because you know how to do that, of course, everything.
But maybe
mostly, I mean, how this kind of category theoretic type of reasoning of thinking that is mostly based on morphism and composition can help derive or find the equivalent of that result in quantum computation, of the decomposition of a unitary into one qubit and two qubit operations. That is what I was trying to add.
Yeah,
I think that
I get it.
That my intuition is that this is an important problem, that if it can be solved and then technically realized, that is going to change things. It's going to change the whole field.
So the starting point for that is to look exactly for suitable building blocks. Maybe they are not all, maybe they are only some, because again, the ZX calculus started with a few ingredients. It didn't have everything from the start. It was a problem open for many years to figure out which rules. The building blocks were universal quite quickly, but the rules weren't. So we didn't know all the rules that would allow you to derive everything that you wanted. So now we do. And you might not like the style of some, you prefer some others, but still there's options, which is good. But the first thing is find some suitable Lego pieces that you can then compose into bigger processes. And
but there we go. You put there an example, about the CX calculus. Of course, the CX calculus was known, before. But the fact that you're applying the thing, I think that is based on the fact that there was a big contribution coming from Rauschenberg and Briegel, that they said that there was another way of doing computation that is a measurement-based computation. And when you look at the measurement-based computation and you think a little bit, you realize, oh, it's a CH pack.
yes,
Indeed.
and it was one of the first. Correct.
That's a big leap.
In the the idea that the ZX calculus was that could represent one-way quantum computation or measurement-based quantum computation with, say, the cluster state. That was already in the fairly early papers, and what came later and was substantially different was the observation that actually the basic building blocks of the ZX calculus are the operations of lattice, of surface code lattice surgery. That came later. That was Dominic Horstman and.
But what I'm trying to say is that the big, I'm a physicist, not a mathematician. The big leap is the fact that someone comes and tells you that there is an equivalent model to the circuit model that is measurement based. And then you start looking at the structure and say, aha, that is a structure.
Yeah. Correct.
Let's use it.
Correct.
I mean, because it's not obvious to make that leap.
No, it isn't.
I mean,
Of course, it's a very for a long time. I think I was discussing this at lunch with Adrian. There was this no-go result on error correction.
Yeah.
That just said, yeah, absolutely. There is no way to perform error correction on quantum computers, and nobody really read for quite a few years. Nobody read the subtext, which said, unless you allow CPTP maps that can depend on measurement outcomes, and then you can.
Exactly.
But no, everybody was like, okay, this is the you can't do it, whatever. There's a fine print in the theorem that you can sort of go around and. But yes, MBQC was. I think MBQC is one of the big big applications, but the ZX calculus can be used to reason about anything, can be used to reason about dynamical systems and Schrodinger's equation and the Weil canonical commutation relations, which take a particularly nice form. I was talking about it yesterday. And I will talk about it in actual lecture later on. So yeah, there's lots of models, and making models for interesting physical theories is just, it's a mindset. I think that's the real shift, is that you stop thinking, what is inside my systems and how do I calculate with it? And you start thinking, what can I do with my systems and how does that compose? And that shift of perspective makes you see bigger things in a simpler way, because some of these things are so big that it's very hard to look at them from the, I'm going to give you one example. The algorithm for the hidden subgroup problem, which is the one that breaks most of, actually all abelian cryptography. You draw it as a diagram, or you write it down, you try to write down all the building blocks. It takes a long time because you have to imagine what it means to do addition, modular addition, how do you write the circuit. Even just with the circuit formalism, it's a big circuit. Or you can write it as a diagram, and then it looks like this. That's it. You know what the pieces are the ones of the ZX calculus, but they hide that this thing is C over some really large system, and this thing is C over some really large group. Let's say Z2 to the 2048, right? And this is similar. So it's humongous, but the basic rules that tell you how the ZX calculus works on those groups are the same for all groups. They are even infinite ones.
Well, but infinite, but okay. But I mean, if you have SU2.
Yeah, it has a similar structure, but SU2 is not a commutative group.
That's the point. That's exactly the point.
The algorithm doesn't work but the algorithm is written the same way. It's just that when you try to do the and I did go through this in the past a few years ago with Alex Kissinger, where we gave a completely graphical, so purely diagrammatic proof that this algorithm works without using anything other than equations between diagrams, to show that you don't need to put anything else. Like the equations of these calculi are enough to prove that the algorithm is correct, including all the group theory stuff that goes behind it. It becomes pretty clear that the algorithm itself works perfectly fine even for non-abelian groups. The algorithm, the quantum part of the algorithm, doesn't have a problem with it. The proof is the same. What fails is the statement that the samples that you get from the algorithm allow you to reconstruct the hidden subgroup. That's the classical post-processing part, because abelian subgroups have logarithmically many generators and non-abelian ones don't. That's like in non-abelian groups, you can't use the fact that subgroups are logarithmically generated, like the Pauli group, right? The fact is, the reason you can do stabilizer simulation is because you have a logarithmic representation of the state. You only need to know logarithmically many pieces in order to do the entire evolution. That's the basic of these classical simulation results. It's the same here. The reason it works for abelian subgroups, but not for non-abelian subgroups, sorry, for abelian groups and not for non-abelian groups, is that in non-abelian groups, the subgroup description can be arbitrarily complicated. And you can indeed prove that for dihedral groups or permutation groups, even in the finite case, this doesn't work. There's papers from a few years ago that say that these strategies will always fail. So yeah, any SU is going to be hopeless, obviously. Obviously. Correct, but you can still write the conserved quantity, the symmetry conserved quantity duality, even for non-abelian groups.
Not necessarily.
For compact ones, you can.
I mean, well, not necessarily, because it depends. I mean, what you mean by non-abelian duality? What I mean is, you know, that local model to another local. So you can go from local to non-local. But going from local to local,
No, yeah, of course. No, sure.
It's impossible.
Of course. I mean, that's because abelian groups are, the duals of abelian groups are particularly well behaved. They're not all abelian groups are self-dual. The finite ones are, but the infinite ones may not be self-dual, but their duals are still nice and well behaved, and they satisfy like finite, compact, finite. They're all, so the theory of symmetries and conserved quantities for abelian symmetries, you can do with the ZX calculus even in infinite dimensions, and it works fine. Like, for example, you can write symmetry observable duality, and you can prove that the same map that gives you the evolution is the map that gives you the measurement. If you just take it upside down, you do the adjoint and you get the measurement instead. So that's quite convenient. You can do a lot of nice diagrammatic reasoning about measurements and time. And if you want, I can later on in the week, I can talk about it.
Some diagrammatic things, just for students here.
What would you like to see?
Diagrammatics for some duality, some dual thing.
Like time energy?
You show some diagrammatic for duality, some dual.
So imagine that you have, okay, let's start with you have a Hilbert space. Any? Really? And you have ut defined to be e to the I t th over h bar. So th over h bar. I don't know. I'm going to absorb it into the Hamiltonian for simplicity. So any continuous time evolution over it. Now there's a trick that you can use. So you could write this as, you can say the time is a classical parameter, which is the standard way to start. You say this is it's a one parameter group, like in Stone's theorem. You can write a map that has a quantum system here. And I don't know why I suddenly lost power. Okie dokie. And then you can say, okay, here I have a classical parameter, which are represented by a dashed wire, which is just the real numbers. And I define this map, this block, I'm calling it U, and I define it by saying that if I apply it to the classical state for any given time, t, it's my unitary. So I just packaged my unitary. There is nothing special about it yet. What is special is what happens when I quantize it. I'm going to take it and I'm going to say, okay, I have this map. And if you allow me enough latitude to consider integrals and unbounded operators, which are well defined but unbounded, I can move it and I can quantize it. And I can say I consider the same map, but where the control system is not classical anymore, but instead is L2R. And that is well defined, but of course, necessarily unbounded. It has to. But you can still do a lot of, the category underneath is well defined. So you can do that. And now you can, again, apply it to the state, the delta over some value. And that gives you your unitary. And again, the fact that this state here is a delta function tells you that this operator is unbounded. But it's a position eigenstate for it's a one-dimensional parameter, and these are the position eigenstates. You're saying, instead of saying I have a classical operation where I have an analog parameter that I can put in, you say I have a quantum operation where the control system is sort of the quantized parameter space. But now because you quantized it, interesting and good things happen to you. So you consider ZX calculus for that, for L2R, where one copies the time and the other one adds the time. So one is, it's the group operator, it's the group algebra over the L2 function. But you technically don't even care about L2, you just take C and say I take all linear functions, including the unbounded operators, and then it's good. So you have this, and now you say, what is the property that defines this unitary operation? Like, how can I talk about this kind of dynamical systems diagrammatically? And the properties are three. You have three axioms, and they define exactly the operation. One says that if you apply it to the unit, you get the identity. That's the same as saying that U0 is the identity. The second one says that if you apply it twice for successive time shifts. So ST, that is the same as applying it once for the sum of the time shifts. And this is UT composite US is UT plus S. That's the second axiom for the semigroup. And now here you don't really have to, because these delta functions form a basis, you can just remove it and write it like that. It's a bit nicer. And the third axiom, which is the one that says that this is not just a representation, because these two just say it's a representation, but you don't want a representation. You want a unitary representation. You want your one parameter group to be a unitary representation of the real line. And then you're saying that if you take your map and you adjoin it, you want to get something like UT dagger is equal to U minus T, right? And so you want UT U minus T. So somehow you have to write the minus, which is the antipode of the Hopf algebra that comes with this. The group algebra is an inverse. It's the one that sends T to minus T. And on the right-hand side, you still have to have the same types, right? So you just take the cap, and that's the equations you get. So these define exactly the one parameter unitary groups. Exactly all of them. They're exactly the unitary representations of the real line onto your system. So they're all the possible dynamics. And now you say, okay, fantastic. And you're going to have to, luckily, you're going to have to trust me on this because I've not yet given you all the axioms, but I'll give them to you tomorrow. Now you take this and you say, okay, I want the same box, but what happens if I take the box, adjoin it? So now the system goes up. What happens if I now measure it, but in the other basis? So what happens if I measure it in the basis that is dual to the time basis? What is the basis that is dual to the time basis? You get some energy levels, which are in the Pontryagin dual of Pontryagin, I guess, dual of the reals, which luckily is isomorphic to the reals. So it's a real number effectively. And what you get here is just this kind of post-selection. And what it really does is it selects, it's the projector. You can prove. There's a proof of this, which I'll give to you, that this is the projector on an energy eigenspace. So what this map is doing, it's a map that when you then measure it in the energy basis, you get the projectors onto the correspondingly labeled energy eigenspaces. So this thing here, this is the von Neumann pre-measurement. And the full thing with the measurement inside is the non-demolition measurement, is the energy non-demolition measurement. So the same box that you use that defines the dynamics for your system, you take its adjoint, it becomes the box that defines the energy measurement for your system. So if this is time translation, this is the energy measurement. But if this is space translation, this is the momentum measurement. And you can prove that this is a measurement purely diagrammatically. You don't have to do any calculations to do it. Why? Because you can decide, you can figure out what the axioms for a measurement are. What are the axioms for a measurement? Well, if you take the measurement and you sum over all of the projectors, what do you get? The identity, right? So if you take the sum over all the values of E of the projector on E, because this must be a complete family of orthogonal projectors, then this is the identity. What is the sum? It's this. That's the co-unit for the energy observable. So this is just the identity. That's true. That's one of our axioms, is just daggered. We just took we flipped it upside down, but it's one of our axioms. So that's okay, done. then what is the second axiom that it satisfies? Well, first of all, they have to be orthogonal and they have to be idempotent. We don't know that they're projectors yet. We don't know that if we measure one of the energy values, we get a projector. So we can prove that. What does it look like? Well, it says that if we do the measurement twice, then it is the same as doing the measurement once and copying the result. So copying the energy basis result, that is this. That's also the axiom of so. So check. Finally, this is stating two things. It's stating that PE prime is equal to PE delta E prime. That's what it says. And then is the final result that says that these projectors have to be self-adjoint, right? That's the last thing that because they have to be projectors effectively. And so you want to prove that if you take the projector for any value of the energy and you adjoin it, what you get is, so you want to prove this for every, but so you want to put this. And that is the same as saying that if I take this and apply this cup, I get that. It's the same. Now I can apply the cap to both. I don't know what happened, but it's going to be fine. I apply the cap to this side and I apply the cap here. And then I use the fact that if the cup of one color and the cap of the other color is the definition of the antipode, and that is also, that's a third of the axioms that define the symmetry. So if you take the three axioms that define a unitary representation of any abelian group, but in fact of any group, and you flip them upside down, or any bialgebra, I should say, not really group, and you flip them upside down, then what you get are the axioms that define a measurement. So it is a measurement of some kind. It could be degenerate, but it is a measurement of whatever dual quantity your group has. So if it's an abelian group, then the dual in the bialgebra of an abelian group is always the Pontryagin dual. If it's not an abelian group, it depends. But bialgebras are special because they're certain compact matrix quantum groups. So not all non-abelian groups have a nice bialgebra structure in them. And they all have a nice bialgebra structure, but they don't all have a nice interpretation for what the dual space means. But yes, that's about it. That's the proof that if you take, there is no, to get a symmetry observable duality, all you have to do is you have to have a bialgebra of some kind, which gives you the group and its dual. And you have to have the axioms of a representation on the group. And if you just flip it upside down, that gives you the axioms of the measurement for the corresponding conserved quantity. And you can also prove that this measurement is invariant under translation, because actually it's very easy to prove. So let me prove that if I measure a quantity, right, and then I translate my system, that has to be the same as first translating, and then first translating, sorry, and then measuring. I want to prove that that's the case, and that's fairly straightforward. All I have to do is flip this with using the axiom that I had before. That, and then I can glue them to put them together because it's a repeated translation. So it's going to be this and this. And then I want to open it, but I can use first commutativity. So let me go to a different slide to do it, because this is a bit crowded maybe right now. No, fine. Hang on. Let's go here. Let me make it slightly smaller. So I then use commutativity to say, and here is where commutative groups are actually important. I shift the cup on the other side. Now I reopen it, and I have U at the bottom and this at the top. And then I reapply the axiom, that the adjoint axiom, so the unitary representation axiom, and I get this. and I'm done. So this proves that the measurement that, okay, this is, you have a representation you get for free from diagrammatic reasoning only, that its adjoint is a measurement. It's a measurement for whatever quantity the dual basis, so whatever quantity the copy of the co-multiplication is obviously observable, whatever quantity that observable refers to, that's the thing you're measuring. And it proves that that quantity is invariant under the action of your representation. So it's you are measuring something which is a conserved quantity. What conserved quantity depends, but definitely it is a conserved quantity, and you are measuring it. And that's purely by, you said the 3 axioms for a unitary group, everything else is free.
And we need to conserve the speed for tomorrow.
Yes, I'm done.
It's just the first day. So is there anybody who comes tomorrow that doesn't have a book? Tomorrow morning? I will give you a book. You come in the morning, please reach out the 2 spiders. So we thank you so much for coming here, and we have to stop.
4 o'clock. I'll see you tomorrow.
45 across the hallway.